Namaste. Let us start lecture 2 of week 8. So, in the previous lecture, we have talked to you about GMR and we gave you the origin of GMR and how it is being used. Let us see the next round of developments. So, in today's lecture, we will introduce the concept of colossal magnetoresistance. So, when GMR was discovered and reported, lot of interest was generated in this area and both academia and industry started looking for new materials, new configurations, new form factors by which you can increase the magnitude of magnetoresistance. So, as the work went on, people started discovering materials where the change was not just let us say between 10 to 80%, it was by few orders of magnitude. So, those kind of materials were called as colossal magnetoresistive materials, because here the change in the magnetoresistance was even much higher than the GMR materials or configurations. And as expected, large number of materials were discovered. So, we will also discuss some of the initially investigated CMR materials. You will find that it is important to understand the phase diagram of CMR materials and how you can synthesize new CMR materials would also be discussed in today's lecture, and if time permits, I will also discuss about some of the applications. So, we have seen that magnetoresistance is a phenomena where resistance changes on application of magnetic field. And you can actually now classify the magnetoresistance into ordinary magnetoresistance. The concepts which I discussed in the initial part of the previous lecture. So, this OMR is caused by the deflection of the charge carriers due to the Lorentz force. Q dot E plus Q dot V cross B. So, because of this Lorentz force, you see deflection in the path of the charge carriers, and that is effectively the phenomena of scattering, and you see resistance. So, OMR at room temperature is quite negligible, because here already you are seeing significantly high impact coming in from the thermal energy. Then you can have anisotropic magnetoresistance, that is called AMR. This is the resistance which depends on the angle between the direction of the current and magnetization, which modulates the precession frequencies and are mostly found in ferromagnetic metals. We have seen the concept of GMR, where change in the resistance with respect to the original resistance on application of external magnetic field can be of the order of 10 to 80%, and this is due to the spin dependent scattering in multi-layered or composite structures which are formed using a ferromagnetic element and a non-magnetic metal. And we have seen the applications. So, today we will be discussing about CMR, where you will see that the resistance would change by several orders of magnitude. We will see why it happens, and the origin lies in the structural modifications of the materials which we are utilizing to observe CMR. For example, material like lanthanum calcium manganese oxide or lanthanum strontium manganese oxide. So, if you look into the CMR, what is happening? This is the schematic representation of CMR. It is a property of some materials where their electrical resistance changes significantly in presence of magnetic field due to the strong coupling between the metal insulator transition and a magnetic phase transition, and this could lead to resistance changes by few orders of magnitude. Some of the materials where such phenomena are observed are perovskite types magnetites, manganese based perovskite oxides like LSMO, lanthanum strontium manganese oxide, and the initial perovskite material which is modulated to get such LSMO or LCMO structures are lanthanum manganese oxide. So, what happens? It is a perovskite structure, which is an AbO3 type structure. So, the A which is at the cube edges are rare earth or alkaline earth atom, B is manganese, and the phase centers are oxygen. So, in pure form, LMO does not show any CMR. It does not show CMR because here you have the manganese in 3+ state, which is a stable 3d4 high spin configuration state. This exhibits the Jahn-Teller distortion leading to delocalized electrons. but there is no double exchange mechanism which is necessary for CMR. So, you have a very stable system and you do not have elements which are going to respond strongly on application of magnetic field. So, now you have a trivalent atom, let us say manganese, or you have a system which is lanthanum. So, now what you do, you dope it with a divalent atom like strontium or calcium. So, you have strontium which is 2 plus, or you can use calcium which is 2 plus. So, in LO, what do you have? Lanthanum is in 3 plus state, manganese in 3 plus state, oxygen in 2 minus state. So, the total positive charge becomes plus 6. You have 3 oxygens effective. So, you have negative charges minus 6 and therefore, you have the charge neutrality condition. But now, what you do? You actually dope the system. Now, you are replacing, let us say, some of the trivalent lanthanum atom by a divalent system. Now, effectively you do not get plus 6, you have actually plus 6 minus delta charge. So, you are not reaching the state where your positive charges are equal to the negative charge and you have a system which becomes charged, and that means you will have an unstable material, because the fundamental concept is that for a material to be stable, it should be charge neutral. So, what can happen? Because of this loss of charge neutrality, manganese being a transition element can stabilize in plus 4 state also. So, what happens? Some of the manganese will transform to plus 4 states, so that it can compensate for the electropositivity loss due to the doping of strontium 2 plus. So, what you lost from introducing a divalent atom will be compensated by the transformation of manganese 3 plus to manganese 4 plus, and again you can reach the condition of charge neutrality, and hence La 1 minus X strontium X manganese oxide becomes a stable system, where X is the concentration. So, you can have different doping concentration. So, this is the reason why you can again get the charge neutral state. You can have a system like LCMO or LSMO. So, now when there is an formation of Mn4 plus ions, This enables the double exchange interaction, and the moment this is possible, you get the interaction that leads to a ferromagnetic to metallic transition, which is critical for observing the CMR. And it is not that you see very high CMR values throughout. It is observed in certain region of the doping concentration. So, in between, let us say the dope samples where you are having 20% calcium, or on the higher side if you have 40% calcium, that means lanthanum 0.6, calcium 0.40, manganese oxide. This is where you will see large magnetoresistive effects. On either side, the impacts are much lower. Immediately you will ask, why is this happening? If this composition is showing magnetoresistance which is changing by few orders, 10 raised to the power 2, 10 raised to the power 3 orders, then why it is not happening at, let us say, a concentration of 0.1 or 0.9 dopant concentration? What is the reason behind it? The origin of that lies in the phase diagram, which we will see in few minutes. So, if you actually plot the variation of resistivity as a function of applied magnetic field, you will find that, let us say, around 33% calcium doped LMO displays nearly 1000-fold change in the resistance with the application of 60 DC magnetic field. So, you see huge change. If you look into the temperature dependence, then you again see that the resistivity in these systems also change as a function of temperature. So, both is happening. You are seeing change in resistivity as a function of applied field and also as a function of temperature. This is actually coming in due to the phase diagram of LCMO. So, if you look into temperature versus composition graph, so this is X. So, when you have 0% calcium, you have a system which up to very high temperatures, let us say 100 to 300, this is the scale we are talking about, is showing you a ferromagnetic but insulator type system. And you see this composition which is maintained even to concentrations, let us say you are going up to 12% or so. You are still in the range of ferromagnet insulators. But if you are going to temperatures beyond, let us say, 160 degrees or so in this range, then you are transforming to a paramagnetic insulator. Now, in the composition range, let us say somewhere around 12 to 24, 25, you see a system which is maintaining the insulating character, and but the transition temperatures are changing. So, the change from insulating system or a canted spin structures to paramagnetic insulating structures are changing. Then comes a region between, let us say, 25 to 45, where you have the formation of the structure which is behaving like ferromagnetic metal, and that character is maintained till very high temperature. For example, if you say you are talking about a system which is around 35% dopant concentration, then the transition temperature would be around 260 degree. Below this 260 degree K, the system will continue to show a ferromagnetic metal like behavior. Above that, it will go to a paramagnetic insulator. Then comes the region where you have ferromagnetic, but an insulator type behavior, and hence the resistance change is minimal because you are already in the insulator type behavior. So, the structural changes which are associated with them leads to the modulation in the resistivity. So, it is the structural modification in the unit cell that drives the change in the resistance, more so in magnetoresistance, and the change is of the order of 2 to 3 folds of magnitude, but in certain composition range. Similarly, you can have a phase diagram for LSMO, and here also you can go from various behaviors and you can get different types of, you can get a canted insulator type structures, and then beyond the Niels temperature you have a paramagnetic insulator, or in the range which is, let us say, 0.17 to 0.48, you have a ferromagnetic metal like behavior with strong temperature dependence. Beyond that, you have a antiferromagnetic structures. So, you can get various types of structures, and therefore, by modulating the unit cell, you can get modulations in the response characteristics. So, it is now you can make these materials quite easily. We have seen that you can make perovskite structures very easily, and you can make various types of perovskite structures. You can modulate different crystal lattices, and hence you can find large number of new materials being fabricated routinely nowadays, and leading to their applications for magnetic sensing, the reed switch, the Hall effect based magnetic sensors, or magnetoresistive sensors. You can also use them for magnetic proximity sensors, because you have high sensitivity in these systems to a nearby or applied external magnetic field, and hence they also become useful for spintronic applications. So, CMR materials, because they offer even larger changes in the resistance, especially under low magnetic fields, make them useful for magnetoelectronic as well as spintronic devices. So, I hope you have understood the concept of CMR material. They are very simple materials, they can be easily fabricated and their applications are immense. These are some of the references which would give you even more understanding about the topics that were covered today, and I thank you for attending lecture 2 of week 8. Thank you.